Hello, hello. Hello everyone, and welcome to the sixth tutorial of the course Nuclear Astrophysics. So, we will today cover the most of the materials of week 6, and in the last week we have just started the nuclear burning scheme from hydrogen burning, and just hydrogen burning I did in the last class, and also the cell model, the liquid drop model of the nucleus. So there was some confusion about the pairing term of the liquid drop model in the last class. So I have gone through some books, and I will just rectify so those, I mean, shortcoming which was in the previous slide, previous class. So actually for so at first I will just go through that liquid drop model, that last part, that pairing term only, because what I have done in the last class, that was not actually correct, because that book which I followed, it seems there was some mistake, so I have corrected it. So let me first corrected that part, then we will go to today's, I mean this week's material. So the nuclear binding energy for liquid drop model, yeah, that was written as that binding energy, which is a function of a and z, like a, v, a, as, where a is the mass number. So this I have done term by term in the last class, z minus n, or you can write it a minus 2 n, a to z, that is also okay. And there was a pairing term. Okay, so I told you that depending on the number of proton and neutron, whether they are odd or they are even, it will, I mean, that will decide what will be the pairing term, whether it will be the plus sign or it will be the minus sign. Okay, now I will suggest you to look through in a book, that is, the name of the book is Nuclear Physics in a Nutshell. So I have gone through this book by Carlos A. Bertolini, and it is from Princeton University Press. Okay, so just go to this book if you want to. There they have analyzed, I mean they have written the pairing term in a better way, which I have written like delta by a to the power by some a factor in the last class. Now the pairing term, the corrected part, I mean the corrected version, that can be written as minus 1 to the power z plus minus 1 to the power n by 2 ap by half. So all this term, this was the volume term, this is the surface term, then the this is the asymmetric term, this is the third one is the Coulomb term. So all those are there, and also the pairing term. Now that pairing term, the correct way, I mean the most correct way, is to express it like this way, where your z is actually the number of protons and n is the number of neutrons. It is much more clearer than the last class, because now suppose you have odd number of protons and neutrons, so your z equals to n equals to odd. If this is odd, that means your minus 1 to the power z will give you minus 1, also minus 1 to the power n will give you a minus 1. So that means the numerator, only consider this numerator of this factor, it will be minus 1 minus 1, that means the overall sign will be minus. That is the main point. So for this case, the numerator of the pairing term will be negative. And if your z and n is even, that means suppose 2, that means minus 1 to the power 2 is plus 1, also minus 1 to the power 2 is plus 1, that means your numerator, this part, will be positive for z equals to even and n equals to even. Okay, so that means when both are odd, your pairing term is negative, and when both are even, your pairing term is positive, which is also correct. One student asked that question, so that's why I rechecked my previous notes. So the main point is, when two proton or two neutron two are bound by, then that will be more stable than the single neutron or single proton. That is actually coming by this, exactly this term. Okay. And if your z is even and n is odd, say, that means -1 even z, suppose it is 2 and n is 1. Suppose I am just taking a even value and an odd value, that means it will be +1 and it will be -1, so that will be 0. That means the numerator of the pairing term will be 0, so that the whole term will be 0. Similar case is if z equals to odd and n equals to 1. That means any of the neutron number or proton number is odd and another one is even, then the term will not exist. It will only exist if both are odd or both are even, and depending on the odd and even, that will be positive and negative. Okay, so last time I just have some the students have some confusion, so don't consider the last pairing term which I did in the last class. All the other terms are same, that volume, surface, asymmetry and the Coulomb interaction term, all are same. Just for the pairing term, use this new expression which I have written here from the book Nuclear Physics in a Nutshell by Carlos Bartolini. It is a better book to understand that pairing term. Okay. So now I will just do a very short calculation from this binding energy to give you some idea that and all this constant, this AV, AS, AC, AA, these are all constants, and also here is another constant AP. Okay, so all these constants are, you can note down that those values, that is 15.6 MeV, that is the volume term constant, then the surface term constant, then the z into z minus 1, that means Coulombic term constant, just a second, 0.7 this one, and AP 12.0 MeV. So AP is the pairing term. Okay, and another term should be there, that AA. Suppose I think I have not written that part. AA is 23.285. Yes, AA is 23.285 MeV. So if you can remember, this is okay. Otherwise, if there is any question from the liquid drop model, these values will be given. Now just I will calculate the binding energy, the term by term, to give you some idea of this particular element. Okay, Br, sorry, this element. So for this element, the A is 80, your Z is 35, that means your N is 80 minus 35, that is 45. Okay, so let us calculate the terms. So the volume term at first, which is AV times A. AV is given 15.56 into A is 80 for this particular nuclei, so that will be 1244.8 MeV. This is the volume term, that is the first term. Now coming to the second term, the surface term. So AS is given 17.23 times 80 to the power 2 by 3rd. Okay, which will give you, and also I am taking this negative sign along with this calculation. Okay, so negative sign is inbuilt in this calculation, that is minus. So minus 319.9 MeV. This is the surface term. So you can see that volume term is 1244 and the surface term is 319. So the dominant term is mainly the volume term, and all the other terms are correction. As I told you in the previous class, it is coming as a correction. So for the Coulomb term, it will be 0.697 times Z into Z minus 1. So Z is 35. So 35 into 34 divided by 80 to the power 1/3, right, which will be minus 198.2 MeV. So I am writing this to give you some idea of the different terms. So volume term, surface term, Coulomb energy term we have done. Now the asymmetric term, the asymmetric constant is 23.285 MeV, and what was the term? That was Z minus N square. Okay, so your Z minus N, it should be Z minus, yeah. So that means 45 minus 35 square, that is 10 square, divided by 80. that will give you minus 29.1 MeV, because all these terms are minus, that's why I am using that minus sign. Okay, and now coming to the pairing term. So for this particular element, n is odd and z is odd, that means we have odd neutron number and odd proton number. So this is valid, so our pairing term will be negative. That will also come if you put minus 1 to the power 35 plus minus 1 to the power 45, that will give you the negative sign itself, and the total value will be minus 12.0 divided by 80 to the power half. Okay, that is minus 1.3 MeV. So you can see the pairing term for this particular nuclei where the odd combination is there, the pairing term is negative, and so only the volume term is positive for this particular element, particular nuclei, and the whatever the element, the surface, Coulomb and asymmetric terms are negative, only the pairing term will depend whether it is positive or negative. Now if you calculate the total thing, the total binding energy, it will come out to be 696.3 MeV, just adding all these different terms, which is volume, surface, Coulomb, asymmetric and pairing term. So this was just to give you an idea that if our element has a odd number of z, odd number of n, how we can calculate the different terms, for the liquid under the liquid drop model consideration. Okay, and it we got from our liquid drop model assumption, and the measured value which is experimentally founded, it is actually 694.2 MeV. You can see how close this is. So our liquid drop model is not a bad one at all, it gives a good value which is experimentally nearby, which is nearby to the experimental values. Okay, so this was the mistake, I will say, the mistake or the confusion which was during the last class, the associated with the pairing term. Okay, so just consider pairing term as I have shown in this lecture, and all the other terms are same as the previous thing. So this correction I should have done at the starting of the today's class. Now we will go to the materials of the 6th week, as this is the 6th tutorial. Okay, so what we have already done, we have already done that resonant reaction, right, the non-resonant reaction, and one thing I have not done yet, that is neutron induced reaction. So I have not done it because you can see after going through the materials for neutron induced reaction of the week, that neutron induced reaction are mainly dominates above the iron peak. That means those elements which have the mass number greater than 56, iron has the 56, they are mainly produced by this neutron induced reaction. That's why I thought that I will do that neutron induced reaction once you get some idea about that P process, R process and S process. So today, this week is a better place to do it. So at first I will do the neutron induced reaction, then we will go to the burning stages, and at last we will go through the assignments also. So I have gone through the assignments. These are mainly theory based assignment. There are no calculations, just one question was there which needed a little bit of calculation. Other questions was exactly asked straightforward from the material of the 6th week. So for a recapitulate, let us go through the material very quickly, then we will go to the assignments, and if you have any question you can ask anytime. Okay, so this confusion has been asked by a student, so I thought it will be better that this pairing term confusion to go through a good book, and that's why I did not tell anything in the last class. I told that I will go through some good book and I will get you some clear idea, which I tried to give it today. Okay, so now coming to the neutron induced reaction. So you have already seen that for the resonant reaction, so for resonant reaction there for non-resonant reaction particularly, our sigma, which is the cross section, that was a smooth function of energy. For resonant reaction, this was not a smooth function. At particular some resonant energy, there was a peak around that peak the most reaction occurs. Now all these things are for a charged particle interaction. Now Newton is not a charged particle, it is a neutral particle. So we have to deal the Newton induced reaction with a separate way, which is not similar as a two charged particle interaction. Okay, so this Newton induced reaction, if you go to the material course class of 4th to 5th week, 4th or 5th I have forgot, most probably 4th week, no, most probably 5th week. So there it has been done. So the actually the cross section of Newton induced reaction can be written as like this, where your gamma are the okay. So what happens here, that a particle that Newton is reacting with the element, and that will create a excited state of compound nucleus. Then that compound nucleus will release a gamma photon, and it will come to a ground state. So it is a two-step process, and what I am telling is actually an example of radiative capture. You know that gamma radiation is actually called the radiative, if the product is the gamma photon, then it is the radiative capture, which has been taught already. So this is the cross section for Newton induced reaction, where Q is the Q value of that particular reaction. Okay, now suppose okay, so that is the reaction. Q value is the Q value of that particular reaction, and En, which is the kinetic energy of the neutrons, and there is some what I will say, there is some constant that your neutrons should have some thermal energy. It should not have very high energy, it should be slowed down, so that it will follow a Maxwell-Boltzmann distribution, and this slowdown is mainly happens due to different type of scattering. Then the neutron slows down, and it will go to other reaction. It will trigger other reactions. So now one condition is there, that Q value for this particular reaction is much greater than En. As I told you that En are thermal energy of the neutrons, and which has slowed down already. So this En is not a very high value. So a typical value of this En is 30 keV. Okay, is a typical value, whereas your Q can be in MeV. So MeV is much greater, 1 MeV is much greater than 30 keV, and it can be tens of MeV, the Q value. So this condition, if follows, then you can write it, this gamma are actually partial width. You have some idea of partial width while you have done the resonant reaction. So I am not going to that part again. So Q plus En approximately, so I should give that approximate sign, we can write as Q only, because En is very less. And that Q value, any Q value of any reaction, if there is a reaction, if it happens anywhere in earth or in space, wherever, the Q value will be constant. So the Q value is a constant thing, and the TnQ, which is the partial width, is also a constant. So mainly the sigma n will depend on this particular thing. So partial width of the neutron, so this is some elementary, is in the some particle B, and neutron is coming from neutron as a projectile, you can say. So at first it will create a compact nucleus around that B. So here it is N plus B, which is have created a compound nucleus. Then there will be a emission of gamma photon, and the nucleus will come to a ground state. So this is the step 1, and this is the step 2. So actually this gamma n En was the partial width of the first step, and gamma n Q plus En it was the partial width of the second step. Okay, so that's why I have drawn that. So this is your condition, this is your dependency condition under the assumption Q is much greater than En. Okay. Now there we will do something that this lambda cut square or reduced lambda square, you can say it is actually h square by 2me from Schrodinger equation. And energy, so that means lambda square is varies as 1 by E, and energy is proportional to v square, because let's consider the kinetic energy. E is equals to half mv square if m is the mass of the particle. So that can be written as 1 by v square as well. Okay, so your lambda square is 1 by v square, and here we will use a simplest scenario, that as this is a resonant reaction, and in the last class I have told you that resonant reaction mainly depends on the angular momentum of the projectile. So if the value of L, if you can remember, which is LH cut is the angular momentum, so L is the angular momentum quantum number. So depending on the L values, the reaction will be different type of, I mean the reaction cross section will be different. If L is 0, it will see a different type of cross section, I mean the projectile. If L is 1, the cross section will change, because I have shown that in a picture in the last class. Sarah has also shown that. So for the simplest case, we are considering the S wave neutrons. That means L is equals to 0, which is the simplest understanding. Now if L is equals to 0, so under this condition, always remember what I am just going to tell you is only valid if L equals to 0. So if L equals to 0, your tau n, gamma n, capital gamma that is, can be written as Vn, which is the velocity of the neutron. So that we are substituting here, that Vn or V, whatever you can say, Vn is for neutron. Only here I am again writing only if S wave neutron is there. That means L equals to 0 neutrons. Only under that assumption, so it will be 1 V will be cancelled out, sigma varies 1 by Vn. That means sigma n Vn will be constant. So this is a very important criteria of important feature or characteristics of this neutron induced reaction, that your sigma V is constant, and it remains constant for a large range of energy. I mean from 1 keV to 100 keV. That this keV is actually the energy range of the projectile neutron. If that is in that range, so your sigma V is actually constant, and you can measure the sigma V at a higher energy, and you can use that sigma V at the lower energy, because it is constant. So that is a special characteristics of this neutrino induced reaction, whereas our sigma V was not constant for non-resonant or resonant reactions for charged particle. Okay, so this is the important thing, the sigma n Vn is actually constant, and it is, again I am emphasizing, under the assumption of S wave. If the S wave neutron, if the neutrons have higher L number, so S wave means L equals to 0, right? And if you have higher L number, L is 1, L is 2, then that will be modified, which I will do here. And another thing here, you can show from there that sigma V is not a function of T. In the non-resonant case, so just for comparison, in the non-resonant case, you can remember our sigma V was proportional to T to the power P, where P was tau minus 2 by 3, if I can remember correctly, just check it. So where tau is also can be expressed as tau square e to the power minus tau. So if we can express the mean sigma V as tau square e to the power minus tau, where tau was your 3E0 by kT, I think with a minus sign. Just check this, these are all from the previous thing. So point I want to mention that for the non-resonant reaction, our sigma V was a function of temperature. Okay, so temperature to the power some P, that P can be calculated by this way. But in this neutron induced reaction, the sigma V is independent of the temperature, which is another difference from the resonant reaction, non-resonant reaction of charged particle with the neutron induced reaction. So okay, so this type of question may come, that you have been asked like which type of reaction depends on the temperature, and there are 4 options, that resonant reaction, neutron induced reaction, and any other 2. So the main answer will be the Newton induced reaction, which is not a function of temperature, under the assumption of L equals to 0. Now, if your L equals to 1, suppose, so up to this point what I told you is L equals to 0. Now, if your L is 1, that is sigma L for non-zero L, that's why I am writing that L here is actually, so the dependency will be like same sigma n as lambda square gamma n. So lambda square is 1 by v square again, but this time the gamma L will not be proportional to Vn, which was in the previous case under the assumption of S wave, under the assumption of L equals to 0. Now this is not valid for L equals to 1. So we have to find out a way to calculate it. So it has been found that for L not equals to 0, gamma L varies as L to the power e to the power L plus half for L not equals to 0. And you can put L equals to 1, 2 here also, no problem. So, and for that case this 1 by v square is there and e to the power L plus half. Okay, and 1 by v square means 1 by e times e to the power L plus half. So the proportionality will be e to the power L minus half, because this e will be divided, so that's why L plus half has become L minus half, and this is now a function of energy. So sigma L is now a function of energy, okay, for higher waves, for L not equals to 1, for higher partial. This is called the higher partial waves. So higher. So Newton induced reaction is always depends whether what is the L value of your Newton which is taking part into the reaction. So if it is like this, we have found that sigma L dependency on E, then from the mother equation, so I always refer it as the mother equation of the sigma V, which we are using from the second class itself, that is E sigma E e to the power minus E by kt d. Can you remember this equation? It was the same mother equation, and we have used the sigma depending on which type of reaction we are considering. For non-resonant it was the S factor, sigma was a function of S factor. For resonant thing it was a function of resonance energy, and for this Newton induced reaction sigma is like this, I mean this one, sigma is proportional to e to the power L minus half. So I am writing the proportional with the proportionality sign, that E is there already and E L minus half. So this is this here, L minus half e to the power minus E by kt d. So this is valid for only Newton induced reaction, e to the power L plus half e to the power E minus E by kt d. So that this will tell you the dependency of sigma V, mean sigma V, on the energy for higher partial wave. But for lower partial waves, for L equals to 0, the sigma V was constant. So this is the main difference for L equals to 0 and L not equals to 0. So for L equals to 0, sigma V was constant. For L not equals to 0, sigma V is a function of energy. Okay, just a second. Okay, sorry. So this was the particular thing for Newton induced reaction. You don't have to bother much about it, because I couldn't find any numerical question from this Newton induced reaction. If we come across any question, then we will solve it. Okay, now yeah, so the main point was sigma V is not constant here, constant in this case. Yes. Generally what we use for the Newton induced reaction, we use the Taylor series expansion. don't bother much about this, you don't have to understand very deeply. So Taylor series expansion, and we express the sigma v as a series, okay, and from there we generally calculate the new all the reaction rate, all the other things of the Newton induced reaction. I will not go into much details of it. So it was the thing. Now let us go to the yes, any question? Okay. So let us go to the nuclear burning. So in the previous class, just let me see the previous class notes if it is here or not. Yes. Okay. Okay. Just a second. Reaction. PT. Yes. So in the last class we have done that hydrogen burning. So hydrogen burning we have done, and as a result of this hydrogen burning, helium has been produced in the last class. So we will go to the higher elements from helium in this class. So actually what happens in that part, that our proton that has reacted with the with another proton at it, and it has created a deuteron. I am not writing the byproducts and neutron and all the other things, just hedonic part I am writing. And again one deuteron can go through reaction with the another proton, and it can create a helium. Also another so it is the first step, it is the second step. Also another thing can happen, two deuterium can react and it will create a helium and a neutron. This was the second step. And the third step was that this I will write the main equation. All the other equations are there, you know, just I am just writing the main equation, I mean the dominant equation. Now 3He will react with another 3He and it will create a 4 helium and 2 proton. So this was our hydrogen burning stage, where 3 substages are there. And what is actually happening in this full process, that 4 protons are reacting and 1 helium has been created, 2Ag4. Okay, 4 protons are creating 1 helium atom. So this is the hydrogen burning. And now we will go to a cycle which is called the CNO cycle. Now remember, this CNO cycle is not similar to carbon burning, nitrogen burning or oxygen burning. This CNO cycle happens itself in the hydrogen burning stage, because as helium has been created, this can give rise to other elements also. But when we will discuss some element burning, that means when we will discuss the carbon burning, then at that case we will just consider a reaction with carbon with another carbon, that is called the carbon burning. So CNO cycle is not the carbon burning or nitrogen burning, so don't confuse these two things. These two are entirely separate things. So CNO cycle is happening in this stage itself. It can happen in other stage also. So CNO cycle is different from the nuclear burning of carbon, nitrogen, oxygen. This is entirely different. Okay, so I had a picture. Yeah, so this is the CNO cycle. So actually what happens, that you have just a second. Yes, so helium has formed, and you know that if there is helium, that there can be triple alpha reaction, which is the alpha reaction means helium nucleon itself. So 3 helium nucleon or 3 alpha can react, and that will create a carbon 12C carbon. So this can be created. And as we are considering the okay, so one thing you can ask, that till now we have considered only that helium has been produced, helium and 3 helium has combined in a carbon nuclei by the triple alpha reaction. I will come to the triple alpha reaction later. So this triple alpha reaction is giving rise to this carbon 12. Then this carbon 12, as it is in the hydrogen burning stage itself, there are plenty of protons. So it will react with another protons and it will create nitrogen. Then nitrogen will go through beta decay, will give you 13C. Then one proton reaction with one proton again that will give. So by reacting with the proton, the mass number is just increasing by 1. You can see that 12C is going to 13N. 13N is not stable, you know, so it is going through a beta decay. It is going to the 13C, which is more stable than the 13N. Then this 13C is again going through a proton collision. The mass number is again increasing by 1, so 14N has been created. This 14N is stable, that is why there is no beta decay in this particular 14N, and it is again, as it is stable, it is again going through a proton interaction, and the 14N is going to 15N, 15O, and this 15O, so 14N to 15O, and this 15O is unstable, because you know that 16O is the stable. So just a second, this was the stable, that is why there is no successive beta decay. This was stable, that is why also no successive beta decay. This was stable. So whenever you are coming, you are interacting with the stable nuclei, your mass number is increasing by 1, and depending on the product whether it is stable or not, it will go through beta decay or another proton reaction. Okay, so as you saw that this 13N, this was unstable, right? So as the product of 12C, which is stable, with proton which is giving 13N, which is unstable, this unstable nuclei will try to gain stability, and whenever you are coming, I mean in the path of CNO cycle, whenever an unstable element is coming, there will be a successive beta decay. So as 13N was unstable, the successive beta decay is here. As 15O is also unstable, a successive beta decay is here, and this type of chain reaction generally occurs. So if you start from 12C, you can go up to 15N. Also this 15N can also go through another proton reaction with another proton, and 16O. So 16O, from 16O, 17F, 17O, this type of reaction, chain reaction occurs. So the first part, that means this half is called the first CNO reaction cycle, and this is the second CNO cycle. So that exactly same thing I have done here. You can see here that if you start with the 12C, which is the result of the triple alpha process, then it is a stable thing, it is taking a proton, then 13N has been created. It is 13N is unstable, it is going through a beta decay. This is the beta decay actually. Okay, so that this is giving to 13C. 13C is stable relative to 13N. It is also again going to a reaction with the proton, which is giving 14N. It is also stable, so there is no successive beta decay. It is again reacting with another proton, which is giving 15O. Now this 15O is unstable. It is successively going through the beta decay, which is giving 15N. Okay, so this type of cycle occurs, and this is called the CNO cycles. And in this CNO cycle, different type of elements, CNO, from the name you can understand this is carbon, nitrogen, oxygen. So carbon, nitrogen and oxygen can be formed from the helium ash, I mean helium core. Okay, so this is the CNO cycle, and not only this particular reaction, there can be many more reactions. It is a some type of gigantic branch, not this simplest branch. So other elements may also form, no problem in that. Now one main point is in this total CNO cycle, and I told you that this CNO cycle is happening in this hydrogen burning phase itself. Hydrogen burning is going on, helium, some portion of helium has been created, those helium is giving rise to carbon, but the dominant process is the hydrogen burning in that particular part. And you can if you calculate the proton numbers, you can see that here is, so let me erase all this thing, we will just focus on the proton numbers. So here is one proton, here is one, here is one, and here is one. So in this CNO cycle itself, these 4 protons can give rise to helium itself, because you can see that 4 protons will give always the helium. Okay, so this can also form in the CNO cycle. That is the indication that CNO cycle is happening in the hydrogen burning stage itself. Okay. So, this was the main thing of the CNO cycle, and one thing I want to mention just yes, and as it is a cycle, so CNO cycle, so focus on this particular term which is cycle, and it can be shown by adding all the abundances in the sun that the CNO abundance is constant. I mean, it will go through like a cycle. So, what amount of carbon, with what amount of carbon it will start, the at the end of one particular cycle the amount will be constant. Okay, that's why it is called a cycle. So, if it starts with 50 gram of carbon, after the total reaction, that 50 gram carbon you will again get. So, that is the abundance conservation, you can say, in the CNO cycle. Okay, now we will so hydrogen burning is there, helium has been created in that particular in the time contemporarily the CNO cycle is happening. Now let us consider the burning of helium. Okay, so that means the triple alpha reaction that we will consider. Now before that I will show you a plot. So this plot. So this plot, you can see that it is, the points are denoting when the burning stages starts generally as a function of temperature as well as the density. So you can see the hydrogen burning happens at first when the temperature is low, the density is also low. Then the helium burning, when the temperature has been increased up to certain level, and all the other elements are at the higher side. I mean, with increasing temperature, the higher and higher order elements has been created. But why this increase of temperature happens in the star? So that is the main point. I will first go through that, then we will come to helium, because when the hydrogen burning is going on, all the hydrogen will be converted to helium, and some of the helium will go to the carbon, and CNO cycle will happen some portion, but not the helium fusion has been started yet, because the temperature is low. Now suppose all the hydrogen has been burnt out, you are left with no hydrogen, then the core will try to collapse because there is no release of energy as all the hydrogen has been gone out, and there is gravitational force also. So gravitational force will make the core contract. Now due to this contraction, there will be release of energy which will increase the temperature of that particular, which will increase the temperature of the particular core. So if this is a core, hydrogen burning is completed, helium burning is going on, it will contract. Just consider, so I am putting a smaller circle. Okay, so this big part has been contracted to a smaller thing because gmm by r square gravitational pull to the center is there, so it will contract, and during this contraction there will be release of energy which will increase the temperature. It is the core. Okay, so the total star is like this, all the other elements are here, but it is the core only, the center, very central part of the star. So this core has been sink down, has been contracted, but the envelope is there. Okay, so what happens that due to the contraction, so you can think it as a not that type of rigid body, it is a collection of gas, so the envelope type thing is there, but the core is being contracted. So there will be release of energy, and that release of energy will increase the energy of the outer part. So this part of the core, the envelope, outer part of the core is envelope. Okay, so that envelope will gain energy, the temperature will increase, as well as the core temperature is also increasing. So the core, as it is a helium core and the temperature has been increased, that helium burning will start at the core. So at the core the helium burning will start, and at the envelope, just suppose there is a circular ring around that core. Here there was no previous fusion or burning, and now the temperature has been increased, so in that particular ring the hydrogen burning will start. Okay, so this may seems a little bit difficult. So the helium core has been generated. Now there is no release of energy, the contraction is happening. Due to the contraction, the temperature of the core as well as the envelope is increasing. So the core will start to burn helium and the envelope will start to burn the hydrogen for the first time. The hydrogen burning in the envelope has been started just due to the increase of the temperature, because in the star the central temperature will be much more than the surface temperature. So as you know, for sun itself the surface temperature is only 5000 Kelvin, but the core temperature is 15 million Kelvin. That's why the main hydrogen burning starts at the core and the envelope does not take part in the fusion at the starting of the core burning. As the contraction happens, the temperature increases at the envelope also, it will start to burn hydrogen and then other elements. So a cell type structure forms. Here will be helium, there will be hydrogen. I mean, if you consider a later evolution, it will be Fe, then there can be neon, then there, I mean, not nickel, yeah, that is also possible. All the other types of elements will be there. I mean, let me write it. Suppose it is oxygen, it is carbon, it is hydrogen. So this is a cell structure which is formed due to the contraction. Okay, so that is the obvious point, that we need a contraction to get a higher temperature that which will eventually start the helium burning. Now how this contraction give rise to the release of the temperature, that is the main point you have to understand. Gravitational contraction, release of temperature, that means nuclear burning of higher elements. Okay, so this is called a virial theorem. I will just go through very quickly that PV is equals to NKT. It holds in the, I mean, inside of a star in any source which is in a hydrodynamic equilibrium, and the thermal energy ETH is 3/2 NKT. This also you know from your kinetic theory of gases just. Okay, so your so you can write from these two equation, your P is actually 2/3 of ETH by V. This you can write. Now suppose you are integrating it with a volume element 4 pi r square dr. So the whole thing, I mean, left hand side and right hand side we are doing the volume integral, and that will give you PV is 2/3 ETH total. That means ETH total means the thermal energy in the whole star, inside of the star, it is there. And another thing, just 3-4 minutes it will take at max, just a second, but I think it is good to give you the idea why the temperature increases with the contraction of the thing, of that particular star. So this is done, just remember it. Now another thing I will do, that dPr by dr is equals to gmr rho r by r square. So this is one of the 4 equations. So for a star, to define a star you need 4 equations, which I have done in the second class. One is for pressure, one is for density, one is for temperature, one is for luminosity. So 4 out of 4 equation I have just written the pressure equation. This must hold. If there is a star, this condition is happening. Okay, and now if I do the integration of this particular equation over the volume of the star, 4/3 pi r cube, that dP dr is there, where dr, I mean, it should be 4 pi r square dr. The same thing, I am just doing the integration over the volume. Okay, so and yes, and here also this part is there. I am not writing this part. This part is there with 4 pi r square dr, and we are doing this integration from 0 to r star. R star is the surface of the star. So if it is a star, it is r star, and it is 0. So if we do this, this part will actually can be divided by 2 different things. and it will give you a result like PR 4 pi r cube 0 to r star. You don't have to remember this thing, just try to get an idea. 0 to r star PR 4 pi r square, it is needed, that's why I am writing. It is coming from the left hand side only. Okay. Now our assumption is that P is 0 at r equals to r star. If you consider this thing and if you put the value, so if you put this r star limit, the upper limit, that will go to 0. So the first term will go to 0 under this assumption that P is 0 at the surface of the star. Only this term will survive. Okay, minus 3 0 to r star PR 4 pi r square will survive. And if you do the integration, now suppose our P is a constant P, it is not depending on the radius, and we are using an average P. So PR, we are using an average value of P. So that will come out of the integration, and the integration will be like this only 4 pi r. It is assumption, simplest assumption, and 3 is there, minus 3 is there. And if you do this integration, then you will be left with 3 p bar 4/3 pi r star cube, right? So this is just the volume of the star. Now this all this value is coming from considering the left hand side only. And the right hand side, what is the right hand side? Right hand side is actually gm rho by r square 4 pi r square dr. Okay. Yes. Now if you do the integration, then you will get that 4 pi r cube. Just a second, I will check it. Oh yes, oh sorry, just a second, it will be r cube r square dr. Yeah, just my mistake, it will be 4 pi r cube. We are going to get a volume average quantity, that's why it is 4/3 pi r cube. Okay, sorry. So that's why is dr will be cancelled out, and your P will be this type of thing. Okay. 4 pi r cube, just let me check. Yeah, so maybe I am doing some mistake here, I will just confirm it, no problem, but try to get an idea. The first term will go to 0, 4/3 pi r cube, 4/3 pi r cube, and there is this is pi 4 pi r square. Yes, no, I have not done mistake. So this 3 and this 3 will be cancelled out, that's why there is no 3 in this particular expression, you can see. And it will be 4 pi, and the right part it will be gm, so this r square will be cancelled out, so there will be one r, and this 3 is cancelled out. 4 pi r gm rho 4 pi r gm rho dr. So this type of thing will be in the right hand side. Okay, now this is actually, and if you do the integration, so that will be gm rho is there, and this r dr will be r square, proportional to some type of proportional to r square dr. So that will actually give you minus rho r 4 pi r square, and you can think it as the self energy of that particular sphere. That means you are taking a shell of a star at infinity, and from that infinity you are bringing that shell into this part, and by accumulating the cell, smaller cell you are collecting from the infinity, you are making the total star. Okay, so that means this right hand side is actually giving you the self energy of that star, okay, which can be written as EGR, which is the self energy. So this part can be written as E of GR, which we will tell as self energy, and you know that self energy is negative, so minus EGR. Okay, now from the right hand side we got this, from the left hand side we got this. I have not gone through all the steps. Now the main point is we have to equate the 3p and 4/3 pi r star cube. I will write it as the volume of the star is minus EGR. Okay, yes, just a second, yeah, EGR. Now 3pv cpv. Okay, now so you can write it as a that your P is EGR by 3 value, and here, so this we will just, this 2 we will just equate, and we will get a result between E thermal total and EGR. So that is the reason, if you just equate this particular two thing, you will left with the result that I will write just a second. So just equate that two, you will get E thermal total is actually minus EGR by 2. This is a form of virial theorem actually. That means if the gravitational contraction is there, it will increase that ETH total. Gravitational contraction means EGR is decreasing, and decreasing with the negative side means it is actually increasing. Okay, so it is a play of that negative sign, which is very important. EGR decreasing means the minus. So suppose EGR the value was 5, so that was yes, EGR is decreasing, that means 5 to 10, because minus 10 is decrease, but the ETH will be plus 10. That means the thermal energy will increase from plus 5, it will increase to plus 10. That is the reason why with gravitational contraction the thermal energy gains happens and the thermal energy increases. Okay, so this was the thing why with the gravitational contraction the thermal rise in the temperature happens. So if this happens, then the helium burning will start at a particular temperature when the kinetic when the kT will be equals to the Coulomb potential of helium reaction, and that will start. Okay, so and helium will give you the carbon 12, which we have been used in that CNO cycle. Okay, so that is the helium burning, and the main point is that this helium burning is happening through double process, double stage process, that is called the 3 alpha process, where in the first part 2Ag4 plus 2Ag4 that will give rise to Be8, and it is a it can happen in two direction, and for this the temperature should be greater than 10 to the power 8 Kelvin. That's what I was trying to explain, because for proton reaction the temperature needed was few million Kelvin, that means few times of 10 to the power 6 Kelvin. That was enough for the proton reaction, but you can see for helium reaction the temperature is needed as 2 order of magnitude, which is mainly coming from the gravitational contraction of the core and rising in the temperature. So that's why I tried to do that. Now this is the first stage. So one thing can happen that this Be8 can go through, can again decay to 2 alpha, and another process can happen that this Be8 will accept one more helium, and that will create the C12 with a gamma. So this is the creation of carbon 12 from that triple alpha process, because here 1, 2 and 3 helium is taking part in this particular process, and that's why it is called the triple alpha process. Now as I told you that it is a reaction which can happen in the both way, the first reaction. So Be8 it can also decay to 2 alpha, then there will be no formation of the carbon 12, because to get the carbon 12 we need the Be8 in the we need the Be8 in the static quasi equilibrium state. That means we need some amount of beryllium 8 to go through the second reaction. If the beryllium is itself decaying into 2 alpha particles, then there will be no chance of the triple alpha reaction. So but this lifetime of beryllium alpha beryllium A, so lifetime is actually 10 to the power minus 16 second, roughly 10 to the power minus 16 second, and the time so 10 to the power minus 16 second, that means up to this time the beryllium will be there, and this is, although it is very small, but this is large enough to go through the third reaction. So if the lifetime is 10 to the power minus 16 second, although it is small, but in respect to this second equation this is long enough, and this Be8 will go through a reaction with another helium which will give rise to the carbon 12. So this is the main formation of carbon 12 in the triple alpha process, which is a result of helium burning also. Okay. So just now to live, yes, and this is the thing, and you can calculate the cross sections of everything, which I will not do now. The yes, now the main point is, which is important, that Hoyle prediction, how this carbon 12 actually yes, or yes. So helium burning, it may be up down, no problem. So in helium burning, as I told you, there is a two step. First beryllium 8 formed, then from beryllium 8 the helium is the carbon is formed. And so here you can see that beryllium and carbon and alpha particle reaction, the second stage, and the Q value of this particular thing is 7.366 MeV. So Q value is 7.366 MeV of that Be plus alpha reaction. Okay. And the gamma peak of this particular reaction is around E0, around 230 to 280 keV. You know that gamma peak, and around this 230 to 280 keV the maximum reaction occurs. Now if you add Q plus E0, that is 7.366 MeV plus, it is in keV, we will convert it into MeV, just take the upper limit 0.28 MeV. Okay, so that will give you 7.640 MeV roughly. 7.366 plus 280, yes, 7.640 MeV, 280. And fortunately Hoyle predicted that the carbon, which is the product of this particular reaction, carbon 12, it has a resonance state around this energy. You can see it has a resonance state, although it is not the ground state, it is some excited state of the C12 nuclei, but it has a state at 7.644 MeV. And here we have also got a value of 7.640 MeV, which is comparable to the 7.644 MeV, and that is the main reason this reaction occurs. If there was no resonance state of 6.4 MeV, 7.644 MeV of carbon 12 at this particular position, then this reaction will not occur, and you cannot create the carbon 12 using this triple alpha process. Fortunately this is there, and Hoyle has predicted that. And also you can see, this is important, that the value of the spin value, parity, is 0 plus. Okay, so 0 plus to 0 plus, so direct decay of 0 plus to 0 plus is forbidden. As I told you that this 0 plus state is an excited state, it will decay into 2 plus, then immediate lower level, and it can again decay from 2 plus to 0 plus. Okay, so that can happen, but the main part is the formation of carbon 12 is exactly because of that existing resonance of 7.644 MeV with the spin of 0 plus, which Hoyle has predicted, and that is the main reason of the abundance of carbon 12 which is coming from the triple alpha reaction. Okay, so this was the important thing. And yes, okay, so this is the main product of helium burning. So helium burning is completed. We have got carbon burning, carbon 12 by the triple alpha reaction, and then we will consider the carbon and other elements eventually. And some other things can also happen during this helium burning stage. That, just a second, carbon burning, neon burning, silicon burning. Yeah, so helium burning is done. Yeah, here, so this figure is important regarding the CNO cycle. Here I have shown, in the previous thing I have shown you this particular plot, and here I have also included all the other elements, that is 18 oxygen, 19 fluorine, 18 fluorine, all can be produced in the CNO cycle, no big deal in that. And another thing, this figure, it is some I mean, I am going to that previous part for some moment. So these reactions, although you don't have to understand anything, so this is actually the reaction which govern the CNO cycle. Okay, so if you consider just one particular reaction, like the reaction of, reaction rate of N13. So N13 is here. N13 is created by 12C. So you can see this is the creation of N13. It has been decayed into beta decay. So that's why this term is there. Tau beta is there. Tau beta denotes the lifetime of the beta decay of 13n, and also this 13n is going to it is 13, yeah, this 13n can go to the 14n also through that 13C channel. So that's why another term is there. So any of the two can happen. Okay. Similarly, for carbon 13, you can see it has created by the 13n. So that's why for carbon 13 equation, the producer is N13 and the destruction is happening through the P decay. So this is the destruction rate. So this is how the rate equation has been written for every element, considering which is the producer of that particular element and which is the decay product of that particular element. So here you can see that from nitrogen to oxygen 17, all the equations are written, and if you equate all the equation equals to 0, then you will get a matrix, and by solving that matrix equation you can get the quasi equilibrium abundance of every element in the CNO cycle. That's why I put it here. It is from some book, but I thought it is interesting. Okay, so and another thing you can ask that I have told you, remember that in the CNO cycle itself, these 4 protons are participating and they can also create a helium. So this is the thing which tells you the energy dependency of CNO reaction and PP reaction. So for PP reaction, the reaction rate goes as T to the power 4. So please allow me to do it. Pardon me for this. It was some back. It is coming from the back actually. So because CNO cycle. So up to some temperature, the proton-proton reaction dominates, and after this temperature, the CNO cycle dominates, because the CNO cycle goes as T to the power 17, but the proton-proton goes as T to the power 4. So after some time, the 17 will took over the 4 power law, and it will dominate. So depending on the temperature, we can say whether the PP is dominating or the CNO is dominating, and sun lies here. So for sun, the PP is mainly dominating in the not the CNO cycle. That's why I told you in the PP burning, proton-proton burning, very small amount of CNO cycle will be contemporary with that proton-proton reaction, not dominant. Okay, but for larger mass it can be dominant, because for larger mass the temperature will be larger, so CNO cycle can dominate. Okay, so we have done the CNO cycle, we have done the helium burning. For remember, proton-proton burning is giving rise to helium. Helium burning will giving rise to carbon. Now we will consider the carbon burning, and in between of this burning, that carbon 12 can trigger the CNO cycle also, which is happening alongside with this nuclear burning thing. And the main reason of creation of this carbon 12 due to helium burning is 7.644 MeV energy state, which is present in the excited nucleus of the carbon 12. Now coming to the carbon, just let me check if I am, it is done. Okay, yeah. So and also in that helium burning, I told you that carbon 12 is formed, and also many other things can be formed. The carbon 12 is the main dominant part. So once carbon 12 is formed, that can also go through another helium atom, and that will create oxygen. This oxygen will also go through another atom, and it will create the neon. So this type of reaction can occur from carbon to oxygen to neon. This can also form. Okay, so this is not CNO cycle, this is separate from CNO, because here the reaction is happening through the alpha particle. But as it has been shown in the class that there is some limitation for the higher elements, so it cannot produce higher elements than the neon. So neon 20 is the last product, you can say, for the helium burning stage. Okay, that part I will not do it, so I just told you. And yeah, so let us go to the carbon burning, and how the carbon exist, how this the survival of carbon, all this you have done in the class. So I will not pay much attention. I will just paying attention to the creation of different elements, and if needed I will come to the survival of carbon part. Okay, but before that let us go to the carbon burning. So once carbon is produced, this carbon burning, as I told you, that burning means fusion of two similar type of elements, that is called the burning. So 12C, as proton burning P plus P, helium burning Ag plus Ag, for carbon burning 12C plus 12C. That's why in the CNO cycle I told you that is not burning, actually it is reaction, subsequent reaction, not burning. So that it can create 24 Mg. Also it can create, I mean there are many reaction possible, neon 20 plus alpha, all these reactions are possible depending on the Q value. Okay, so this all the reactions are possible due to the fusion of 12C plus 12C. Now two of the equation are important because you can see that here is a creation of proton. Okay, so this proton can also react with another carbon and it will give rise to N13. Okay, so N13 there will be a beta decay. Again we are going to the CNO cycle, that will, I mean it is a part of CNO cycle, C13, and the alpha particle which has been created here or here, that can act here. So 2 alpha alpha particle will react it and O16 plus neutron will be there. So this reaction can also happen in the carbon burning phase, and the main part is this neutron. This is the neutron which is required for the neutron induced reaction for the elements beyond iron. So it is one of the source of neutron, because for neutron induced reaction the free neutrons are required. So this reaction is giving you a source of free neutrons. Okay, so that's why it is important. And so as I told you that carbon burning, so here also you can see that carbon burning is happening at a much higher energy because the Coulomb potential is higher. So to overcome the Coulomb potential the temperature must be higher and the contraction, gravitational contraction is happening. So that part which I told you in the gravitational contraction, it is just pictorially represented here. So the carbon, so the core has become carbon here because it is carbon burning phase. There will be helium burning envelope and there will be hydrogen burning envelope also. So the red is the hydrogen burning envelope, the blue is the helium burning envelope, and the black is the carbon burning envelope. So this type of burning happens and it is at the core. You can see this is only this part of the star, and outer envelope is getting getting higher and higher temperature due to the energy released from that core, and due to the increase of the temperature the size of the envelope increases, and that is the main reason of the red giant, because the core has been contracted but the envelope has gone to a bigger size due to the increase of the temperature. Temperature increase means volume expansion. So the volume of the envelope has been increased, expanded, and it has been gone up to a very high radius. That is the main reason of the red giant. So red giant generally forms at the later evolution stage of the star. It will not form in the proton burning phase. It will start to form from the helium burning and it will continue to grow through the carbon burning and the oxygen burning, silicon burning phase. Okay, so that is presented here. Now as I told that in the carbon burning the required temperature is T9 is 0.6 to 1.0. So that means you need at least 0.6 time into 10 to the power 9 Kelvin temperature. So for helium burning it was 10 to the power 8 Kelvin temperature. For hydrogen it was 10 to the power 6 or 7 times temperature. You can see that the rise of the temperature with the higher and higher order elements. Okay, so this carbon burning happens and the products are this type of sodium, neon, magnesium, oxygen, anything can happen. Now as neon has been created here, oxygen has been created, we will consider the burning of this element because it has been already created in the carbon burning stage. So if we go to the neon burning, and neon burning comes into the picture before the oxygen burning, because at this high temperature as I told you, the temperature is almost 10 to few times 10 to the power 9 K. I mean 0.6 times 10 to the power 9 K to 10 to the power 9 K. This is the range of this temperature, and at this temperature the photo disintegration is plays a vital role. So we are now considering a different type of reaction. We had resonant reaction, non-resonant reaction, neutron induced reaction. Now we are coming to the photo integration reaction. So at a high temperature, the photo disintegration reaction is a important thing, and 20 Ne, that is neon 20, it takes actively part in this photo disintegration. That's why the neon burning is very much, I mean, happens very sufficiently, I mean very effectively, not sufficiently, efficiently in that particular temperature range. So because it is very active in photo disintegration. So that's this photo disintegration is the main reason of the neon burning. And what happens that a gamma ray photon that is captured by a neutron, that is called the photo integration, and it will create a excited neon state. Okay, so this type of photo disintegration occurs, and then it will that excited state will decay into different state. So it can go to a higher elements as well as a lower elements. So some examples are 20 Ne, it will absorb a gamma ray and it will create a 16O and a alpha particle. Also this can, so this is the photo disintegration, okay, which is giving rise to 16O. That means 20 Ne has been disintegrated to 16 oxygen by a gamma ray photon. That is why it is called the photo disintegration. That means disintegration due to photons. And this 20 Ne can also react with alpha and give rise to 24 Mg. So this reaction is not photo disintegration. Photo disintegration was this particular thing. This is other reaction which can also happen in this burning state. 28 Si. Also there can be other elements also. So you can see that from neon we are getting oxygen as well as silicon, that we are getting. So now we will come, so neon burning happens in this way. So neon burning will give rise to oxygen, silicon, then this oxygen will again burn because of the gravitational contraction, rise of temperature. Whenever one fuel is ended, the gravitational contraction start to happen and it increase the temperature and further elements start to fuse, I mean take part in the fusion. Okay, so for neon burning, the temperature required is 1.2 to 1.8, the T9 range. So for the carbon burning, the range was 0.6 to 1. Now the range is 1.2 to 8. You can see the range has been increased. And oxygen burning happens at few high temperature, at a very high temperature than this. So for oxygen, the temperature should be greater than this neon burning temperature. So these are the examples, I mean these are the reactions which is happening in the oxygen burning state. I will not go through that. There can be origination of silicon, magnesium, this type of reaction happens, and you can see the Q values are there. So these are not that important, I mean in respect to proton or helium fusion. So this reaction happens and it will giving rise to silicon. So this silicon will again burn, and this silicon burning is also through photo disintegration. So neon and silicon is happening through the photo disintegration part. Okay, and it happens at 2.8 to 49. So temperature is increasing. So this is the silicon burning thing, and higher the elements will happen. So from this silicon up to iron can produce, but beyond iron this cannot be produced by this nuclear fission, or what we are calling that nuclear burning. From beyond iron we need to consider the neutron induced reaction, which I told you at the beginning of the class. So for A equals to 56, that means iron, the neutron induced reaction dominate. I mean not dominance, that is the only reaction Newton induced. Okay. So that part we will do in the later next class. First I will do the assignments and that okay, then another thing is here that I will come. Okay, so let us go to the assignments. Till now I have told you that proton fusion, I mean proton burning, then the helium burning which is giving rise to carbon burning which is giving rise to oxygen, neon, then neon is giving rise to silicon, oxygen can also give rise to silicon, then the silicon burning is processed and it will give higher and higher order elements. Okay, now let us go to the assignments. Okay, so first question was the lifetime for dissociation of 8 Be into 2 alpha particles. Here I have told you that when I did the, where is it, yeah, here you can see, while going through the triple alpha process, the second step was beryllium 8 plus I mean the first step was 2 helium atom will give rise to a beryllium atom, and that beryllium can also decay into 2 alpha particles, but and that lifetime is 10 to the power minus 16 second. This value is important. So that is the question of answer of the first question. All the questions are just theoretical questions. 10 to the power minus 16 second. Okay, just a second. Yeah, now the approximate resonant energy for the capture of 8 Be into 12 C. This also I have told you again and again that this 8 Be plus alpha to C12 reaction happens only due to the presence of the 7.644 resonance state of carbon 12 with 0 plus parity, spin parity. So that is the answer. This is 7.6 approximate, it is given that 7.6 MeV, and the spin parity, see, Hoyle state is that exactly state 7.64 MeV plus with 0 plus spin. That is the Hoyle state which I am talking about again and again. That is Hoyle discovered that. So it is 0 plus. Okay. Now which of these nucleus did not form during Big Bang nucleosynthesis? So I mean this is not a question which should be given here. Now what happens in Big Bang nucleosynthesis? Mainly in that time there was a creation of primordial helium and hydrogen. Okay, and lithium was not formed. So helium and hydrogen can give rise to carbon, that is okay because carbon is a stable thing, but this lithium, you have already seen, lithium is very unstable and it will react with other things, and the presence of lithium is almost negligible. And also in the first class it has been told that most of the abundance of lithium, beryllium and boron is coming from cosmic rays, not from the nucleosynthesis. So that is the answer. I mean you can relate this question to that part, that in the whenever you are going to the nucleosynthesis, lithium cannot form in the nucleosynthesis. I mean it can form like a intermediate step, but eventually it will create other elements, it will not exist in that form. So that is why lithium is not created. Okay. Now which of the following correctly describes the triple alpha process? So I have told you that triple alpha process, so triple alpha is actually 1 alpha which will give you beryllium 8, then this 8 Be again 1 alpha which will give you 12 C, right. So which one describes the triple alpha process better? First of all, it should be 2 step reaction, so not together. 2 alpha particles come together to form a 8 Be, right, which again captures an alpha particle to form a 12 C nuclei, right. So these 2 steps are included in this option number 3, and this is the answer, right. And what was the fourth? 4 alpha particles? No, 4 alpha particles is not coming. 4 proton can react with and it can give 2 Ag alpha, but 4 alpha cannot create a carbon. Okay. Now the transit time of two alpha particles coming out of decay of 8 BE. Okay, this thing I have not mentioned. So okay, so let us go to that creation of beryllium. Is the okay? So this was the creation of the beryllium, and I told you that the lifetime, I mean decay time of the beryllium is 10 to the power minus 16 second. And if you just, I mean I have not calculated it, the transit time of alpha, 2 alpha, I mean this alpha plus alpha, not alpha and alpha, is actually 10 to the power minus 19 second. Okay, so this is called the transit time of alpha. That means 2 alpha is going, I mean how I can say that 2 alpha is transiting each other with a time of 10 to the power minus 19 second, because all the elements are in a kinetic, have kinetic energy inside the star and they are moving randomly. So this transit time is much less than this 10 to the power minus 16 second, which was the lifetime. So that is the question. These are I mean experimentally verified, I think, not any theoretical theoretical expression or understanding. So the transit time of 2 alpha particles coming out of from the decay is shorter than the lifetime of 8b, because this lifetime was 10 to the power minus 16 and this transit time is 10 to the power minus 19, which is less than 10 to the power minus 16. Okay. Now the reaction, again you can see that this is the second step of the triple alpha process, predominantly through J pi equals to 0 plus. As I told you, the Hoyle state has a 0 plus spin parity, so the answer will be 0 plus. So this question and this question are exactly same, the spin parity of Hoyle state. So 3 and 8 are exactly same question, 0 plus, just they have increased the number of questions. Now 9, which of the following is an alpha conjugate nuclei? Okay, so alpha conjugate nuclei is actually your alpha is 4He2. Now if any elements which can be expressed as a multiple of this 2He4, that is called the alpha conjugate element. Now your 16O8, this can be written as a combination of 4 alpha, right? Because this 4 into 4 will give you 16 and this 4 into 2 will give you 8. So 8O16 can be expressed as a combination of 4 alpha particles. That's why it is called the alpha conjugate nucleus. Now suppose you take S7Li. 7Li you cannot express is it, so here should be value, not a fraction. So you cannot make that 4 to 7 by multiplying any integer value. That's why it is not possible. So 7Li is not a alpha conjugate element. If it was 8Li, then you can write it 2 like here, and 2 into 4 will give you that 8. So 8Li may be a conjugate nucleus of that, not 8Li, I should say 8 beryllium is a conjugate of of helium, but not 7Li, and all the other elements are not. You can check that only 16O is a conjugate of the alpha nuclei. And the discovery of lines of which element demonstrate nucleosynthesis is so Newton capture I have not covered today. So but you know that technetium is the main thing which tells us that nucleosynthesis is mainly going on in the stars. It has been told in the first class itself. The technetium is a very good detector of the nucleosynthesis, not detector, evidence of the nucleosynthesis. And there was another question that only this was the question which you have to calculate, that for a temperature it is given, density is given, the x, that means fraction of beryllium and fraction of helium is given. Now we have to calculate the number density of both these elements, and you know that number density can be expressed, it was from second or third week class, can be expressed like this, where Na is the Avogadro number. So this is from the previous material. So see, by A4He. A are the mass number of those particular elements. Now if you calculate N8BI by N4HE. That will be rho Na, all those will be cancelled out, right? Just x8be, sorry, x of 8be divided by x of 4he times a of 4he divided by a of 8b. So this, yeah, this is the thing, and the values are given. It is 2.6 into 10 to the power minus 10, and it is 0.25. Now for 4he you can write it as 4, but it is a approximate thing, but because the atomic mass is not exactly 4, so you can multiply it with the mass of the protons in AMU unit, just it will be 4002603. This I have been taken from some reference, I mean you can do it, no problem. So that is, it will give you 5.2 into 10 to the power minus 10. So if you take 4 and 8 instead of that too many decimals, you will not, I mean you can see the options are order of magnitude different. So instead of 5.2 you may get 5 into 10 to the power minus 10, but order of magnitude will be same. So for this question 4 and 8 itself is okay, not 4.002603. okay, so this is the answer, 5.2 into 10 to the power minus 10. So this was the main assignments of this week. It was a matter of just 10 minutes. Now one thing I will do, as I have done the assignment, that so up to silicon burning we have also done. So one thing I have not done yet, that is survival of C12. The creation of C12 I have done with that triple alpha process, but the survival of C12 I have not done it. Okay, just remember that. But I think the important thing is I should give a brief overview of the Newton induced reaction today. So this is the Newton induced reaction. So let me see if I have, yeah, I have page. So sorry, so as I told you, if A is greater than 56, then this reaction dominates. That Newton dominates not, this reaction actually takes place. So what happens, suppose there is a nuclei, it will interact with a neutron, and as you can see Newton is 0 and 1, that means charge is 0 and its mass number is 1. So this, if it captures the neutrons, the new element which suppose be, okay, no, okay, so suppose this is A and not A, suppose X and Y, and it has a mass number of A. So X nuclei type of X with mass number A, it is going through the Newton induced reaction. So the combined nucleus will have a mass number of A plus 1, right? So in this Newton induced reaction, what we actually get, if we start with the ZA element, that is Z is the proton number, A is the mass number, the proton number will not change, that will remain Z, but the mass number, as 1 Newton has been added, it will increase by 1. So this type of reaction mainly occurs in the Newton induced reaction, but it can go even further, A plus 2 by successive steps. So in each step one atomic number will be added. Okay, so this is similar like proton equation, but in proton equation the Z will also increase, Z will increase by 1, and the A is the result of the increase in Z, so that is also will increase by a number of 1. Now two thing is possible. So this ZA, this was a stable nuclei and it was the parent nuclei, say, and it is the daughter nuclei which has been created, or the product nuclei you can say. So it has been created. So it is actually ZA plus 1, the Y thing, and it has been started with ZA. Now depending on the stability of the product nuclei, it has been divided into two parts. This thing I have also told you in the CNO cycle that whenever the product is unstable, it was going through a beta decay and getting the stability. But if the product is stable, then there is no need of that beta decay, and it will just stay there, I mean, and it will react with the other elements, but no beta decay. Beta decay is only necessary when the daughter nuclei is unstable. The same thing happens in this neutron induced reaction also. If the daughter is unstable, then there can be two process, that is, one, tau n gamma is greater than tau beta. I mean, as I am saying that daughter is unstable, so there will be beta decay. Now if your time scale of beta decay, which is tau b, is much shorter than your another neutron capture reaction. Okay, so this is the time required for another capture of neutron, that means to happen this second step, and this is the time of the beta decay. So if the neutron capture time is greater, then the product which is Z a plus 1 will decay beta, because it will get sufficient time to decay a beta as the neutron reaction time is larger. That means it is like this way, I mean, like you want to go to school, and your school will start in 10 minutes, and your breakfast time is 15 minutes. So it is obvious that you cannot have your breakfast if your school starts in 10 minutes. But on the other hand, if your school starts in 1 hour, you can have your breakfast peacefully. You will spend 15 minutes, then you will go for your school. So that is the same thing. If your neutron capture time scale is larger than the beta emission, then the beta emission can happen because it has sufficient time, and it will decay with that beta. So it is called, and this process is called the S process. S process means slow process, and this slow is coming because the second reaction, which is the second neutron capture reaction, has a very large lifetime. That means, suppose you have a particle, neutron has been absorbed, that this is unstable, this has decayed beta and gone to a stable state, and it is waiting for another neutron to come and to interact, because tau n gamma is much larger. Okay, so that's why it is called a slow process, because the process is slow. It has been created, it is going through the beta decay, then it waits for another neutron to come and to go through the another neutron induced reaction. On the other hand, and the condition is your neutron flux is also low. That's why the daughter nuclei have to wait for another neutron to come. But if your neutron flux is high, and also this condition holds, that your time to react with another neutrino is smaller than the beta decay time, that is the second condition. Your school will start in 10 minutes and you have the breakfast time of 15 minutes, so you cannot have that breakfast. That's why the daughter particle cannot decay a beta, and it will instantly go through another neutron reaction. Okay, so let me just put it this way. It was X, one neutron is coming, it reacts with this, and the nucleus is created. It is unstable, and it has a beta emission time scale smaller than the another neutron capture time scale, so it will decay the beta. After decaying the beta, it is coming to a stable state. Then it is waiting for the neutron flux, because the neutron flux is low. Suppose this is the region from where the neutron flux is coming. This neutron flux is low, and it is waiting to another neutron come, then this neutron will again come, then it will go through another reaction, and this chain happens. So due to the wait time, I I'm trying to give you the trying to give you the uh, basics, how this happens. So this stable nucleus is waiting for another neutron to come, and it is waiting and waiting, so it is a slow process. Now the second process, neutron x, so it should be plus, right? It will give a unstable, daughter. So at first the daughter is unstable in both cases. The point is whether that is decaying beta or not. And suppose from this region the neutrinos are coming with a high flux. So you can see the neutrino flux is much higher here than the previous case. It is much higher. So this particle will not have time, because as soon as it has been created, another neutrino will come, then another neutrino will come, because the flux is higher and it don't have to wait for another neutrino to come. The wait time is very less. That's why it called a rapid process, the R process. So that is the main reason why the name is slow and rapid. So what will happen in this second step, that successively it will go through rapid neutron reaction, and it don't have time to go through the beta decay. After all the reactions has happened, the neutrino flux has been decreased. At a later time the neutrino flux will be exhausted, then it will go through the beta decay. When it can get time to do that beta decay, so that beta decay will happen at the last stage. While in the S process the beta decay is happening in each step, but in R process the beta decay will happen at the last, after the neutron flux is exhausted. Okay, so that is the main difference between the slow process and the rapid process. And also this condition happens, this condition is the same, that beta decay time and the lifetime, which one is in greater, and the neutrino flux. So two conditions, both are important. One is the lifetime, another is the neutron flux. Okay, so this is the main thing. Now this S process, so this is the R process, as I told you. Here the flux, neutron flux is also high. Flux is high, and here neutron flux is small, not small, low. Okay, so this S process generally happens in AGB type star. So AGB is not a separate type of star. AGB is some phase of the star, we used to tell that it is a red giant phase, white dwarf phase, or red supergiant phase, this type of phase. Similarly AGB is a phase of a star. So if the star is in that phase, that is called the AGB star. It is not a different type of star, it is a phase of its lifetime. And this R process can happen in neutron star. Why? Because I told you that a high flux of neutron is required, and neutron star is made of neutron. The flux is much higher than other astronomical object. So this neutron star will give rise to R process. Also supernova generally type 2. So this is the place of the R process. So S and R both process happens, and in the next class we will see that how this process leads to the projection of different elements. Okay. Now one thing, okay, so it was the S process and R process. So one thing I have not done today, I think you all know that the survival of carbon, again I am telling. So survival of carbon, if you want I can do it in the next class. It will be a recap of 10 minutes or 15 minutes. And one thing I myself will check while I did this calculation, this particular calculation, the temperature increase due to the contraction, maybe some expression I have written wrong. This 4/3 pi r cube or 4 pi r square, there was a confusion. So I will go through that again from any good book, and if there is any mistake I will let you know. But the understanding what I told you with contraction, the release of energy, that is more or less same. Okay, So that I will recheck, and just let me once let me check it here. 4/3 pi r cube dpdr, there will be cancelled out. 4 pi r cube, nice, -3, yes, I think it is okay. It is okay now. It the factor will be 4/3 pi r cube, not 4 pi r square. Okay, so actually, I mean, it was gm rho by r square times 4/3 pi r cube, and this 3 cancelled out that 3 in the left hand side, and I think now it is correct. Still I will check again. I am telling you, I will still check again whether if there is anything wrong. So this was the thing which I wanted to cover today, and here I have just put a picture of the red giant. As I told you that when the hydrogen core is there, the red giant phase has not started. It will start only when the helium burning. So here you can see this image, helium burning, helium core, it is written helium core, that means helium burning has started. So when the helium burning is started, the temperature has increased in the envelope. Envelope means this red part, okay, this is the envelope. So it will expand according to the volume expansion rule, and with more or more burning, the you can see in the third step the red part has become a very large volume, and it will go to the red giant and red supergiant phase, but it will start from the helium burning, not from the hydrogen burning. Okay, so if we just want to get few 3-4 lines, I mean summary, that is, today we did Ag plus Ag 8b. Due to the resonance state of carbon 12, 8b will again react with the helium, so for Ag, that will give to 12c. This was during the helium burning phase. There can be other elements also, I am just writing the main elements. This 12c will again, just a second, I have written it. Yeah, just confirm. Yeah, so this 12c can give rise to Mg, Na, Ne, oxygen, any of the elements. Then those neon will again go through the photo disintegration, and it can give rise to oxygen, magnesium, silicon, this type of elements. Then oxygen will also go through some reactions, and it will give rise to different elements, that is silicon, sulfur. This silicon will again go through burning, and it can make up to iron. So this type of different stages of burning was there. This is the short summary if you want to take from this class. Okay, so this is, and also the important thing is, with increasing of temperature we are getting higher and higher elements. So this is I am showing just to give you the idea that with higher temperature the carbon different elements burning starts. So this was the main takeaway of this class. Now if you have any question you can ask, otherwise I will end this class, and if required I will do that survival of carbon in the next class. Also I have given you that pairing term of the cell model, that I forgot, pairing term in a more corrected way. Okay. So these are covered in this particular class. Okay, now if you have any question you can ask, or today sorry, I will end this class. Let me just check another thing. So which here it is fine. Okay, so if there is no question, so we can end today's class and we will meet next week. Okay. So thank you for joining.